Hi everyone, I'm Jiawen Liu from University of California, Merced. In this talk, I will introduce our recent work, Sparta, a high-performance framework for element-wise sparse tensor contraction on optane-based heterogeneous memory. This work is collaborated with PNNL and William and Mary. This paper was published in PPOP 2021. Sparse tensor contraction has been widely used in quantum chemistry, quantum physics, deep learning, and so on. Optimizing the performance of sparse tensor contraction has the fundamental impacts in the industry and academia. This is an example of low-dimension tensor contraction, which generalizes that a matrix times a vector. This slide shows another example of a high-dimension tensor contraction in which a three-order tensor times a vector. This slide shows an example of sparse tensor contraction. There are non-zero elements, and the elements are stored in a sparse tensor format. However, how to efficiently compute sparse tensor contraction has three challenges. The first challenge is that the size and the non-zero pattern of the output tensor are unknown before the computation. In this example, the number of non-zero in the output tensor J is 1. However, the size of the output tensor J becomes 4, though the size of the input tensors X and Y remain the same. With the same size inputs, the size of the output becomes 4 from 1, which demonstrates that the size of the non-zero pattern of the output tensor in sparse tensor contraction are unknown before the computation. The second challenge is that irregular memory access along with multidimensional index search to the second input tensor and accumulator introduce performance problems. The third challenge is that a large amount of memory consumption caused by large input-output intermediate data with significant pressure on the traditional DRAM-only machine. This figure shows the memory consumption of sparse tensor contraction with 15 datasets and 3 modes on optane-based heterogeneous memory system. We can observe that sparse tensor contraction can easily consume hundreds of gigabytes of memory. For example, datasets Chicago in 2 mode and Flickr in 2 mode consume more than 600 gigabytes of memory. The memory performance and capacity become the bottleneck. To address the above challenges, we built Sparta. Sparta is a high-performance framework for sparse tensor contraction on optane-based heterogeneous memory. Sparta addresses multidimensionality challenges by has table-based approaches and solves the issues of irregular memory access and agnostic memory expansion by dynamic allocation, permutation, and sorting. To address the memory capacity limitation, Sparta uses static data management on optane-based heterogeneous memory based on analytical modeling, workload characterization, and avoidance of unnecessary data movement. Sparta achieves 28 to 576 times speedup over state-of-the-art sparse tensor contraction and up to 98% performance improvement over the state-of-the-art data management solutions on optane-based heterogeneous memory. Sparse accumulator, or SPA, is a popular approach in sparse matrix multiplication, which uses a sparse representation to hold indices and non-zero values of the current active matrix law to do accumulation. Like traditional SPA, SPTC SPA has 5 stages, and those stages are significantly customized for sparse tensor contraction. Let's see those stages one by one. The first stage is input processing, in which the input tensors X and Y are permuted and sorted. The commutation includes 3 stages. The first stage in the stage 2 is the index search, which searches the corresponding contraction mode indices in the second tensor based on the contraction mode indices in the first tensor. The stage 3 is the accumulation stage, in which we use the sparse accumulator to store the intermediate results and accumulate intermediate results. Our sparse accumulator introduces a thread private dynamic object to store the output tensor from each thread to achieve efficient parallelism. The stage 4 is the write-back stage, in which we write intermediate results from the sparse accumulator to the output tensor J with dynamic allocation. Combined with the accumulation stage, those 2 stages address the change of unknown size and non-zero pattern of the output tensor. The final stage is the output sorting stage, which is optional depending on whether the generated output becomes the input of the next sparse tensor contraction or not. Though this approach is efficient, we observe that the index search and accumulation stages dominate the total execution time. The figure below shows the experiments on sparse tensor contraction with 12 datasets and 3 different modes. However, more than 99% of the time is spending on index search and accumulation stages for 12 datasets and 3 modes. This is still the bottleneck. To address this challenge, we propose hash table-based approaches based on a large number of representations for the second tensor and accumulator to fundamentally address the challenge of multidimensional search in sparse tensor contraction. In the input processing stage, Sparta does not permute or sort the second tensor Y as the previous approach does. Instead, Sparta converts the second tensor to the hash table-based representation. In the index search stage, we first convert the contraction mode in the first tensor to the unique key, and then search the corresponding value in the second tensor hash table, namely HTY. In the accumulation stage, instead of using the dynamic arrays as the previous approach does, we also employed the hash table-based representation for the sparse accumulator. We then use the 3 modes stored in the Y hash table to be the key to search the corresponding intermediate results in hash table accumulator. Finally, we write the intermediate results in the hash table accumulator back to the output tensor. The hash table-based representations solve multidimensional challenges in sparse tensor contraction. This figure shows the memory consumption of sparse tensor contraction with 15 datasets and 3 modes on Optane-based heterogeneous memory systems. We can observe that sparse tensor congestion can easily consume hundreds of gigabytes of memory. For example, datasets Chicago and in 2 mode and click in 2 mode consume more than 600 gigabytes of memory. The memory performance and capacity become the bottleneck. To address this bottleneck, we employ the emerging Atom-based heterogeneous memory, or HM. The HM system includes 2 types of memory, which are slow memory with persistent memory module, or PM, or fast memory with DRAM. The default and efficient mode is memory mode, and we use app direct mode. Compared with DRAM, PM has slightly inferior latency and bandwidth. The challenge here is that how to efficiently employ sparse tensor congestion on Atom-based heterogeneous memory. Currently, there are some solutions. The first natural solution is to deploy the whole computation on DRAM. We call it DRAM only. This approach can achieve the optimal performance. However, this approach is easily out of memory and the program crashes. The second natural approach is to deploy the whole computation on PM. However, this approach causes performance degradation due to inferior latency and bandwidth. The dynamic migrations are the most popular and state-of-the-art solutions. Dynamic migration can be implemented by hardware or software-based solutions. Memory mode is an example of the hardware-based solution, which tracks the page's access frequency and manage DRAM as a hash cache for PM. IAL is an example of the software-based solution. This approach is published in SPLOPS 2019. IAL tracks the page hardness and uses 2 FIFO queues to decide the page migration. However, those dynamic migration solutions cannot work well for sparse tensor congestion because they are application agnostic and can cause unnecessary data movement. For example, the performance of Sparta is not sensitive to the placement of the input tensors X and Y on the PM and DRAM because of their sequential read patterns. But the dynamic solutions can unnecessarily migrate them to a DRAM for high performance. For another example, the hash table-based representation, HTY, has a random access pattern. Any dynamic migration solution cannot efficiently capture its pattern and hence cause a significant data migration. Sparta leverages sparse tensor congestion algorithm guided data management instead of using the state-of-the-art dynamic data management. Sparta employs static data management on Atom-based heterogeneous memory to avoid unnecessary data movement. To motivate our solution of data placement on heterogeneous memory, we analyze the performance of placing major data objects in either PM or DRAM. In this figure, the y-axis refers to the total execution time. The x-axis shows the data object placed in PM. All in DRAM means all data objects are placed in DRAM. We have 3 key observations. First, performance difference between read and write matters a lot. For example, the data object JLocal is write only and the data object Y is read-only. Placing Y in a PM can achieve 18% performance improvement compared to placing J local in Optane. Second, sequential and random access have large performance difference. For example, data object Y is a sequential read-only, and HTY is random read-write and read-only. Placing Y in PM can achieve 31% performance improvement compared to placing HTY on PM. Third, the performance is not sensitive to the placement of some data objects on PM. For example, placing X and Y on PM has similar performance compared to placing all data objects in DRAM. Based on our observations, we introduced the following designs. First, based on the observation 3, we consistently place 2 input tensors to PM based on the read and write patterns. For the rest of the 4 data objects, we prioritize the placement of the following data objects in DRAM according to their importance to performance. To implement the above data placement strategies, we must estimate the memory consumption of the 4 data objects and decide whether they should be placed into DRAM or not. We built some analytical models to estimate the memory consumption of the difference of the 4 data objects. In the evaluation, we employed Intel Optane DC PM server configured with the Intel Xeon Gold CPU, 96 GB DDR4, and 7 68GB Intel Optane DIMMs per socket. We also test Sparta on a general Linux server on Chameleon Cloud configured with Intel Xeon Gold CPU and 96 GB DDR4 per socket. We compared the performance of Sparta to sparse tensor contraction with sparse accumulator, iTensor, IAL, Intel Optane memory mode, DRAM only, and Optane only. The datasets are from FLOPS, NWCAM, and iTensor. The peak memory consumption of the sparse tensor contraction on datasets is more than 600 GB, which is pretty high. This experiment is performed in the Chameleon Cloud server. Compared to the traditional sparse tensor contraction with sparse accumulator, we observed that Sparta brings 28 to 576 times the speed up for different scenarios and cases. We have 2 takeaway messages here. First, hash table-based solutions can fundamentally address the challenge of multidimensional problem in sparse tensor contraction. Second, dynamic allocation, permutation, and sorting can address the problem of unknown output tensors and also significantly improve the temporal and spatial locality. With our proposed algorithm and memory heterogeneity-aware data management, Sparta brings actual performance improvement on heterogeneous memory with DRAM and PM over a state-of-the-art software-based data management solution, a hardware-based data management solution, and PM only by up to 98%, 28%, and 65% respectively. Our takeaway message here is that sparse tensor contraction algorithm guided static data management brings performance improvement on heterogeneous memory over dynamic data management solutions. In short, Sparta is the first high-performance sparse tensor contraction framework on Optane-based heterogeneous memory. Sparta addresses multidimensionality challenges by has-table-based approaches and solves the issue of the irregular memory access and agnostic memory expansion by dynamic allocation, permutation, and sorting. To address the memory capacity limitation, Sparta uses static data management on Optane-based heterogeneous memory based on analytical modeling, workload characterization, and avoidance of unnecessary data movement. The evaluation shows that Sparta brings 28 to 576 times speedup over the sparse tensor contraction with sparse accumulator and achieves extra up to 98% performance improvement over state-of-the-art data management solutions on Optane-based heterogeneous memory. Sparta is open source, and you can download Sparta from this website. Thank you.